So here's theorem 5-3. It's something you're going to prove yourself in your homework. But I just wanted to show it to you here. So it says it's the converse of the perpendicular bisector theorem. So basically, instead of saying if a point is on a bisector, it's equidistant, then it is equidistant from its endpoints, from the segment's endpoints. You're saying if a point is equidistant from the endpoints, then it must be on a perpendicular bisector, right? So we're flipping the hypothesis and conclusion, and that's what gives us a converse, right? If you remember back to that terminology way back when. Okay. All right. So basically, if we have a segment and we have a line that goes through, and there's a point on this line, and that line happens to be equidistant from those endpoints, that means that this must be perpendicular and it must be a bisector. Okay, so that's basically what it says. All right, so hopefully that's intuitive. And remember that not all converses of theorems are true, right? The theorems themselves are true, but remember, converses don't always have the same truth value as the theorem. So this is one that is true. All right. All right. So here we have line L and point P, and P is not on L. How would you determine the distance between P and L, between any point and a line in general? And you want to make sure it's the shortest distance, right? Because we could say, there's an infinite amount of ways we could draw a line connecting these, right? Like, this if line L is a line, it goes on forever, right? So really, we could say that there's an infinite distance. They're infinitely far away. But if I want to try to find the shortest distance, there's only one way to make the shortest distance, and that is the perpendicular. Okay, that's going to be the shortest distance. All right, and a way to just quickly informally prove this is if you draw any other distance, you know that this has to be more than this, right? Because what you have here is a triangle, and in this triangle, it's a right triangle, and this other side is the hypotenuse, right? The hypotenuse always has to be longer than either of the legs, right? And so the shortest distance between a point and a line is the perpendicular distance from the point to the line. Okay? By the way, or you could say is the length of the perpendicular segment, something to that effect. All right, so next vocabulary word, angle bisector. This is a word that we know, right? We've used before, but an angle bisector is a line array, a line ray or line segment or plane that divides an angle into two congruent angles. All right, so it could be a line array, a line segment, or a plane, and it divides a segment or divides an angle into two congruent angles. So here we're going to prove the angle bisector theorem, theorem 5-4 in the book. So it says if a point is on the bisector of an angle, then the point is equidistant, there's that word again, from the sides of the angle. Okay, so if a point is on the bisector, then it must be equidistant, must be the same distance away from the sides of that angle. Okay, that kind of makes sense, right? Because it's right in the middle, so it should be the same distance away. But let's prove it. So we're going to start with the given. So we're given QS bisects angle PQR, right? So that's the that is the first part of the hypothesis there. The point is on a bisector. The second part is not really part of the hypothesis, but we're trying to find the distance between S and those other two lines, and so we need the perpendicular, right, in order to find the distance. So we're saying, hey, this is a perpendicular line here, so that's the distance away from S to QR and S to QP. All right, so let's see. SP, segment SP perpendicular to ray QP, and segment SR is perpendicular to ray QR. All right, so we got these here. All right, so now those are the givens. So now we can use these givens, right? We'll start with the bisect. So bisects, just like we talked about on the last slide, means that it creates two congruent angles, right? So we know that this angle is congruent with this angle. So we can say angle PQS is congruent with angle S or RQS. And that's by definition of bisects, of angle bisector. Okay. All right. And step 3. So now we can use these, right? So we have perpendiculars. So now we can say that they're right angles. So we can say that QPS, angle QPS, and angle QRS are right angles. And we can say that by definition of perpendicular. All right. Okay, so now we can go a few different ways. We can say that these angles are congruent, right? And I think that's probably how we want to go, because we already have an angle here, right? So if we were going hypotenuse leg, we'd want another side instead of another angle. So if we have another angle, then we can do angle, angle, side, right? And so for step 4, I'm going to say that angle QPS is congruent to angle QRS. And the reason is all right angles are congruent. Okay. And then for step 5, so I got these congruent. Now I can use the reflexive property, right? Even though that's already marked on there. So I can say QS is congruent to QS by the reflexive property. All right, and so now we have what we talked about. We have angle, angle, side, right? Angle, angle, side. And the same thing, angle, angle, side here. All right, so we can say that triangle PQS is congruent to triangle RQS by angle, angle, side. Okay, and then now we can say, well, these distances have to be the same, right? This distance and this distance, because CPCTC. So I can say SP is congruent to RS or SR, and that's by CPCTC.